Hello guys, welcome back to my channel Gamma Digamma. So in the past couple of videos, we started building towards proving um, much of the important trilogarithm identities, and in this video I would like to prove the last trilogarithm identity. So as always, let's get started. Okay, so now this is not gonna be more of a proof, it's gonna be more of an evaluation. So we have the trilogarithm of z plus the trilogarithm of 1 minus z plus the trilogarithm of 1 minus 1 over z. We need to evaluate this. So what I'm going to do is I'm just going to keep the simple first term as it is and then write two of these terms in terms of their integral representation. So integral from 0 to the argument 1 minus z logarithm of x over x dx, and in case you're wondering where these guys come from, please check out my last video. Dilogarithm of x over x dx. So now what I want to do is I want to make this upper bound more civil. So instead of having 1 minus z, I want to have like a single variable like z. So for that I'm making use of the substitution x equals 1 minus y. So we have trilogarithm of z plus, so when x is 0, y will be 1, integral from 1 to z dilogarithm of 1 minus y divided by 1 minus y, and dx turns out to be negative dy. So we have a negative up front dy, and I would like to use a similar substitution for this guy. So I would let x equal 1 minus 1 over t. So because of that we have now integral from 1 to z dilogarithm of 1 minus 1 over t divided by 1 minus 1 over t, but then dx this time is dt over t squared. So dt over t squared like that, and we'll have a positive because that was originally there. And now what we're going to do is actually simplify some things. So we basically have taking the negative in, then flipping the order of the denominator, dilogarithm 1 minus y divided by y minus 1 dy. This we can simplify as integral from 1 to z dilogarithm of 1 minus, I can change the variable from t to y again, 1 over y divided by, we'll have y minus 1 divided by y, and one of those cancel out with one of those. So y minus 1 multiplied with an extra y because of the square dy. Now what I want to do is actually apply partial fraction decomposition on this guy over here. So we just have trilogarithm of z plus integral from 1 to z dilogarithm 1 minus y divided by y minus 1 dy. Now applying partial fraction decomposition is pretty trivial on this guy. We have integral from 1 to z dilogarithm of 1 minus 1 over y divided by y minus 1 dy minus integral from 1 to z dilogarithm of 1 minus 1 over y divided by y dy. Okay, So now what I'm going to do is I'm going to take this term and take this last term, the first and the last term, and I'm going to call them G for group terms. So we just have G plus, now we can take these guys under a common integral and a common denominator. Integral from 1 to z, dilogarithm of 1 minus y plus dilogarithm of 1 minus 1 over y divided by y minus 1 dy. When noticing the sum we have in the numerator, it looks familiar, and actually there was an identity like this. So the identity went like dilogarithm of 1 minus 1 over z plus dilog of 1 minus z was actually equal to negative natural log squared z over 2. So if we get to apply that over here, we have g plus integral from 1 to z, plus will now become a minus half natural log squared y divided by y minus 1 dy. And what I'm saying, just keep this expression as it is for now, and let's evaluate this g group term on a fresh page. So I'm saying let's evaluate this guy on a fresh page. See you there. Okay, so all I've done is just written the definition of the g, the group term. So that's trilogarithm of z minus integral from 1 to z of dilogarithm of 1 minus 1 over y divided by y dy. And now is actually a good time to express this trilogarithm in terms of its integral definition. Integral from 0 to z of dilogarithm of y over y dy plus integral from 1 to z dilogarithm of 1 minus 1 over y divided by y dy. Now I would like to break this 0 to z interval as 0 to 1 plus 1 to z, and I'm doing this because I will now have both this and this guy which I'm writing under a common region of integration, which is basically 1 to z, and they also have a common denominator. That was actually the entire reason of grouping them, the common denominator. The other expression had like y minus 1 and stuff in the denominator, so we didn't want that. We wanted a common denominator and a common integral now after splitting, so that we can group some terms. So we have integral from 1 to z, dilogarithm. Oh, I'm sorry, this has a negative over here. Dilogarithm of y minus dilogarithm of 1 minus 1 over y, everything divided by y dy. Now, is there an identity for this difference in the numerator? Well, I can be certain that there was no direct identity, but let's just write all the identities if we can, find an expression for this. So we know dilogarithm of z plus dilogarithm of 1 minus z is actually equal to pi squared over 6 minus a natural log of z times natural log of 1 minus z. That's actually the reflection formula for the dilogarithm by Euler. Second identity we know is dilogarithm of 1 minus 1 over z plus dilogarithm of 1 minus z is equal to minus natural log squared of z over 2. And we want to find an expression for dilogarithm of z minus dilogarithm of 1 minus 1 over z. So if you call this equation 1, if you call this equation 2, we basically have to do 1 minus 2. So when we do that, this guy and this guy will basically go off. So we just have dilogarithm of z minus dilogarithm of 1 minus 1 over z is actually equal to pi squared over 6 minus natural log z, natural log of 1 minus z, and I believe we have a plus now because of the minus, and minus will become plus natural log squared z over 2. That's actually the identity that we were looking for in the first place. So let's make this substitution over here on top. So g is now integral from 0 to 1 dilogarithm of y over y dy, and if I substitute these three terms in the numerator, I can split this main integral in terms of these three integrals by linearity, right? So I'll have integral from 1 to z pi squared over 6y dy minus integral from 1 to z natural log z, natural log 1 minus z, well, let's call it y, since that was our original variable, dy plus half integral from 1 to z natural log squared y over 2 y dy. Well, now this first thing, this first integral that we've been carrying around, let's write it in terms of um, a trilogarithm. This is the trilogarithm of 1, right? Because always the top number was always the argument of the trilogarithm. Now we can integrate this easily. Pi squared over 6 times natural log of y evaluated from 1 to z minus integral from 1 to z natural log of y natural log of 1 minus y divided by y dy, and then this guy, I think there's no need for this 2, we already took that out, is just going to be 1 over 6 natural log cubed y evaluated from 1 to 3. This is basic substitution. You can try it on a piece of paper if you want. Now the trilogarithm of 1 is actually the series sum from k equals 1 to infinity of 1 over k cubed plus, well, natural log of 1 is 0, so ignore that. We have pi squared over 6 times natural log of z. Write this integral as it is for now. And the second term again, natural log of 1 is 0, will be 1 over 6 times natural log cubed of z. Now this is actually related to the Riemann zeta. It's actually a special particular value of the Riemann zeta function. It's the Riemann zeta of 3, which is also called Apéry's constant. So we have Riemann zeta of 3 plus pi squared over 6 times natural log of z plus 1 over 6 times natural log cubed of z minus integral from 1 to z natural log of y natural log of 1 minus y divided by y dy, and this was precisely g. Now what I'm going to do is I'm going to actually use integration by parts on this guy. So naturally I'll be integrating this, and the other bit which is not circled I'll be differentiating. So as a consequence of all this, let's write the integration by part step first. Minus half natural log squared of y times natural log of 1 minus y evaluated from 1 to z minus minus plus integral from 1 to z half natural log squared y is always there divided by 1 minus y, but you also have to multiply by a negative because of the chain rule. We have a negative y as the derivative of this, and then it's all the other terms, so like Riemann zeta of 3 plus pi squared over 6 natural log of z plus 1 over 6 natural log cube g. So at z, it's nice. This has actually a nice form at z. Well, at 1 we have a natural log of 1 which is 0, natural log of 0 which is infinity. 0 times infinity situation which can be resolved using L'Hopital's rule to 0. And let's write this guy as it is minus, or rather have a plus, suck in the negative, correct the order of the denominator, y minus 1 dy, and the rest of the terms are as it is, 1/6 natural log cube g. That's essentially the group terms expression, the g expression. Now it's actually time to plug this back into our original evaluation. Okay, so on this fresh page, all I've done is uh, written the original left hand side that we sought to evaluate, and then express that where we ended on the very first page, the group terms minus this, minus half of this integral. Well, we know for a fact that the group terms are actually Riemann zeta of 3 plus 1 over 6 natural log cube z plus pi squared over 6 natural log of z minus half natural log squared of z times natural log of 1 minus z, and uh, we had to add this guy, half of integral from 1 to z natural log squared y divided by, well, uh, y minus 1 dy, and this guy, apart from the g, all this that I've written until now was g, minus this half of integral from 1 to z natural log squared y divided by y minus 1 dy. And the thing is, we don't even need to evaluate these dumb integrals because they just cancel off, just giving us finally, and I'm going to write this as legitimately as possible, trilogarithm of z plus trilogarithm of 1 minus z plus trilogarithm of 1 minus 1 over z is actually equal to Apéry's constant, or Riemann zeta of 3, plus 1 over 6 times natural log cube z plus pi squared over 6 times natural log of z minus half of natural log squared z times natural log of 1 minus z, and that's it. This is actually the famous, you can call it the reflection formula for the trilogarithm, because it has terms like trilogarithm of 1 minus z, or you can call it the triple trilogarithm formula. The name's catchy, but again, a really really nice relation. you know it's very useful for doing other stuff, like calculating some other things. Okay, so I hope you enjoyed this video, guys, as much as I did. If you have any doubts, recommend me in just you can ask me in the comment section. And I would just like to point out that I don't think anyone has made like so much detailed content in terms of trilogarithm identities. That's why this is probably YouTube history over here. This is YouTube history taking place, and be proud you're part of it. because if you search trilogarithms now, all any YouTube user, any YouTube viewer is going to see is three of my videos first, and then I think one dilogarithm video of Michael Penn. That's why this is like a big moment, and I think that's a good place to end this video. So before going, I would urge you to like, share, and subscribe to my channel. Recommend me to your friends. Spread the word of Gamma Digamma in the math community. Um, it's been a great journey, calculating, proving these identities of polylogarithms in general. Let's see where destiny takes us next. And in the meantime, stay home, stay safe, keep doing math, don't get bored in lockdown, and stay tuned for more content. Peace out, signing off.